Hi everybody. Just thought I'd do a string recognition problem or two for you. We're going to start by typing in, by doing a state 0, which will represent our reset state. If we get a 0, we'll go to state 1. If we get a 1, we'll go to state 2. Similarly, states 3, 4, 5, and 6 will be used for 0 and 1, 0 and 1, and then what we'll do is go to a reset state. This would be a directed acyclic graph except for the bottom arc. Which makes a cycle. And we'll do this with a Mealy machine, so our state transitions will output something. Generally it'll be 0 unless we find a string that we're looking for. So for example, if you're looking for 0, 0, 1, 0, 0, 1, then what you would do is you would output a 1 stroke 1. Here you output a 0 stroke 0. Here you output a 0 stroke 0. If you said to me, I also want to find 7, which would be 1, 1, 1, then you would traverse 1, 1, 1, output a 1 over in here, go back to the reset state. And if you said, I also want to find 1, 0, 1, then you would say 1, 0, 1, output a 1 over in here, and otherwise go to the reset state. Everywhere else you're outputting 0. So now 0, 0, 0, 0, 0, 1 outputs a 1. This does not. 1, 1, 1, outputs a 1. 1, 0, 1 outputs a 1. So those are the 3 strings we plan to recognize. What we can do is we can write a present state, next state diagram. With an output. And in the present state, we'll have states 0, 1, 2, 3, 4, 5, and 6. I could write an S in front of them, but that doesn't really add anything. For next states, if you are looking at x equal 0 or x equal 1, it'll be 1, 2, 3, 4. Right, so if you're in state 1, it could be 3 or 4. If you're in state 2, it could be 5 or 6. If you're in state 3, the next state will be 0, no matter what. And now comes the tricky bit. This is the reset state. Here's the state where you are able to find a 0. Here's the state where you find a 1. If you're in state 3, you found 0, 0. And so it goes. How do you get to state 6? You find a 1 and a 1. And so you're just counting in binary, which is pretty cool. And now let's take a look at the outputs. Now, it says here, if you see 0, 0, 1, here's 0, 0, and then x is equal to 0 or x is equal to 1. So let's assume you're looking for 0, 0, 1. Here's 0, 0. If you get a 1, put out a 1. Otherwise, you put out a 0. If you have 1, 0, 1, here's 1, 0. Put out a 1 or a 0. If you have 1, 1, 1, here's 1, 1. Here's your extra 1. Otherwise, you put out a 0. Here you put out zeros. Here you put out zeros, zeros, and zeros. So now you have your present state, next state diagram. Your next step is to do your row reduction. Your row reduction is going to look for outputs which are the same and next states which are the same. So for example, it looks like states 5 and 6 and even 3 all have the same, well, let's say equivalent impact. So any reference I make to state 5, 3 is equivalent to 5, which is equivalent to 6. And how do I know this? Well, because the outputs are the same and the next states are all the same. So that means I can cross off 6, I can cross off 5, I can rewrite any reference to 5 as 3, any reference to 6 as a 3, and the state machine has just gotten substantially reduced. Moreover, we may look for other equivalencies. Do we see any? And the answer may be no. And if not, let's see. Yeah, I'm not seeing any. We may be done. Of course, we could do an implication chart at this point. But if we were going to do something like that, we might like to do something involving a chart that starts at 1 and ends at 4, and then another chart that another horizontal row that starts at 0 and ends at 3. So let's try that. We'll do the implication chart. So the implication chart starts at 0. It starts at 1, and it's going to end at 4. 2, 3, and 4. The bottom row will start at 0, and it'll end at the penultimate letter, 3. 1, 2, and 3. You then make the lower triangular matrix. And then you look for comparisons. 0 to 1 is true if 1 is equal to 3. We don't know about 1 and 3, so let's look at 1 and 3. 1 is equal to 3 if 0 is equal to 3. Well, we don't know about 0 and 3, so let's look at 0 and 3. 0 and 3 is true if 1 is equal to 0. Let's eliminate some of the things where the outputs are different. We know 1 is not equal to 3 because the outputs are different. So that's helpful. And 0 is not equal to 3 because the outputs are different. And in fact, 2 is not equal to 3 because the outputs are different. And 4 is not equal to 3 because the outputs are different. So that's helpful. Let's look at 0 and 1. 0 and 1 is true if 1 is equal to 3. We know it's not. 0 to 4, we look at 0 and 4, and that's true if 1 is equal to 0. 1's not equal to 0, therefore that's out. Let's take a look at 1 and 2. 1 and 2 is true if 3 equals 3. That's promising. Also true if 4 is equal to 3, but it's not. So that's out. So we look at 1 and 4. 1 is equal to 4 if 3 is equal to 0. Let's see now. 3 is not equal to 0, so that's out. How about 3 and 2? So we look at 3 and 2. We see 3 and 0. 3 is not equal to 0, therefore 3 is not equal to 2. How about 2 and 4? We go through and do a 2 and 4 comparison, 3 is not equal to 0, so that's out. So we have a minimal finite state machine according to the implication chart. That is to say, row matching did a reasonably good job. And in a case like this, it often does. So now we have what I would call a minimal finite state machine for recognizing these 3 strings down in here. Hope you like my little presentation. Naturally enough, if you want larger strings, you're going to need a larger tree, and the tree grows exponentially with the size of the string. Thank you very much.